If you run a simulation in an FEA tool, the default result is almost always von Mises stress. But you can't measure it. You can't put an instrument on a part and read von Mises. It's a theoretical construct. The problem is that real parts, like this crank arm, are being twisted, bent, and sheared all at once. Humankind is doing everything we can to destroy things. It's what keeps us in business. The yield strength comes from this, a simple uniaxial tensile test. We pull a carefully machined specimen in one direction until it permanently stretches and fails. Simple. But a bicycle crank arm isn't being pulled in one direction. The foot is applying a force down, the length of the arm creates a bending moment, pedal offset creates torsion, twisting along the axis. If I'm sprinting along like I'm in the Tour de France, I'm rocking the bike side to side, creating shear. We need a way to convert complex stress into an equivalent simple tension value, and that is von Mises. And it does this by measuring distortion energy. To understand distortion energy, we're going to look at an extreme case that doesn't cause failure. I want you to imagine a deep sea diver. Let's prove it via simulation. I've set up two identical blocks. On the left, a deep sea diver. Hydrostatic pressure pushing in from every side equally. On the right, we have a vice grip. Compression only from the top and bottom. First, look at displacement. Both blocks are moving. The hydrostatic block on the left is shrinking. It's changing volume. Materials generally don't mind this. But the block on the right, it is bulging out at the sides. It's changing shape. It's distorting. Now let's turn on the von Mises results. The hydrostatic block is dead blue. 0 Mises stress. Even though the pressure is immense, there's no distortion, so von Mises says it's safe. But the block on the right is glowing red. That distortion is what tears crystal lattices apart. The math literally squares the difference between the stresses, and so if the forces are equal, like with our diver, the difference is 0. But on our crank arm, the forces are combining, counteracting, interplaying with each other. Von Mises acts as a great equalizer. It takes all that complex twisting and bending energy and converts it into a single number. Think of it as a universal translator. It takes the chaos of the real world, the twisting, bending, and shearing, and converts it into a simple, effective language that your material understands. Simple tension. We use tools just like this every day to figure out why things break. If you want to see us apply this math to real-world disasters, from exploding tanks to sci-fi monsters, hit that subscribe button. I'm Clay Brittain. Stay frosty. C4 is out.